I do have finals. And she was like, what? Like, yeah, she was like shocked. And I was like, yeah. They're like, well, I just thought that you taught like the Stat 2300 and we just didn't have you. And then you also taught that. And I was like, where have you been all semester? Like, I straight up told them, like, I'm a graduate student here. Like, it was really funny.
Okay, so my first plug today is the Mac Club at 5 o'clock, which sort of feeds into this conversation, right? Because maybe you wonder what I do all day, right? I'm no longer a grad student, so maybe you wonder what I do all day. And not just me, what I do all day is actually surprisingly different from what a lot of other people in the school do. So you might show up, it's kind of a fun little talk. It's actually, it was a learning experience for me because even though I've been chair, I got even more of a look at what some of the folks around here do. Mac in. Well, so 8 a.m. No, it's not 10 a.m. And yes, I know. Next year I will think about when the SEC championship is, so I kind of blew it on that. But anyway, so I'll be there. A bunch of other people will be there all day long. Maybe some of you are helping out, or you can just come by. There's also my Mac and announcements. There's a link if you can't be there to Zoom in as well. And also, our final exam is, again, I forget, it's Thursday or Friday, or it's when my classes are. So, when is it?
Thursday.
Is it Thursday?
Could not tell you.
Well, yeah, I usually don't like to give a review sessions the night before an exam, but graduate class is kind of different. How do you all feel about Wednesday?
Proctor, I have a proctor.
Oh, you got a proctor Wednesday, okay.
Jared does too.
How about Monday?
I proctored all night.
Oh,
Are we gonna do it during the day?
Yeah, what time are you thinking?
the day might be difficult because of the fact that there's exams going on. So, when do you proctor on Monday?
I proctored the late one, so if we did it like, I proctored like 7:30, I think, to 9.
I was thinking 5:30 actually.
Oh, perfect, then yeah.
Right, is that?
Because then I could hop
how-
over.
How about all you out there at Etherland? Is 5:30 work on, say, Monday? Okay, good, and obviously we'll be on Zoom too, so, review. I've got to check where rooms are, and we can always pirate a room too. But I think I'll send you all an announcement when I get it.
Is
Okay.
that the one that we were in last time?
Yeah.
Okay.
Probably, yeah. Was I swearing at the computer? The answer to that was no. Probably long 16. So here's the last thing that we did for last time. RB, UFD. Oh, let me make one more announcement. Sorry about that. Did I bribe you all? Did I say that I would give you all an extra quiz score? Well, okay, I'll do that. Everybody gets an extra 100 on the homework if I get like a 90% return or better. Do evaluations. Extra perfect homework with 90% plus response rate. And I've actually got the evaluations open, I think, until throughout finals week, but
It said until the 10th on my email this morning.
when is the 10th?
I think it's
Week
next.
today.
I think
It's
it's
a week
next
from
Friday, it's
today?
next Friday.
My evaluation said till the 10th, right?
Yes,
Yeah, because I think most of them actually
Yeah, they're to
close
the
like,
5th.
yeah, I actually extended it, so. Anyway, so, yeah, so you've got a little time to do that, so make sure you do that. If equals R0, coefficients in R, of course, is of degree at least 1, and P is prime such that I want my prime to do two things for me. Number one, I want P to divide Ri for. So it divides all coefficients except for leading. And I do mean it doesn't divide leading ones. It doesn't divide Rn, and it also doesn't divide R0. I'm sorry, P squared does not divide R0. Then the polynomial is irreducible. And is GCD R0, R1, Rn is 1. That is irreducible in Rx as well. So that was the last thing. This is called the Eisenstein irreducibility criteria. It's very useful. It's useful not only for determining when polynomials are irreducible, but it's also useful for building them. And oftentimes you need to build polynomials that you want to be irreducible. Let me give you, before we do the proof, let me give you an example. Look at that polynomial there, x to the 4th plus x cubed plus x squared plus x plus 1. Show that that's irreducible over zx. Now, you must be thinking that I am having a stroke here because there ain't too many primes that divide the coefficients of that. Everybody agree with that? That's problematic. But check this out. Let x equal y plus 1, and f of x is everybody okay with that? And this is y4 y cubed plus 6y squared y1 y cubed plus 3y squared 3y plus 1 plus y squared plus 2y plus 1 plus y plus 1 which equals y to the 4th plus 5y plus 10 y squared plus 10 y plus 5. so this is 5 Eisenstein. This polynomial right here is irreducible because the prime 5 divides all the lower coefficients except for this one, and the square of 5 does not divide the constant term, so by Eisenstein's criteria, it's irreducible. And if you could reduce this, or if this is irreducible, then the original polynomial is irreducible, because if you could reduce this, then again, change the variable and you'll get a reduction of this. So sometimes you can use Eisenstein, even though it may not look at first blush that you can. So why is this? This is actually a rather famous theorem. Why is this true? So, of R0, R1, Rn is 1, because now a constant does not affect irreducibility. Of f is known Kx. Right? What I mean by that is if I have the polynomial 2x plus 2, 2x plus 2, something simple, then as a polynomial over z, that's reducible because I can pull the 2 out. But pulling out the 2 over q doesn't make any difference because 2 is a unit, right? So pulling the 2 out, I really haven't done anything. Everybody okay with that? So I might as well go ahead and assume this right here. Let's suppose that f of x can be factored into two polynomials in kx positive degree. So suppose with k1 and 2 positive. So in other words, I'm not doing anything silly like letting one of them be a constant. So we can clear the denominators. Well, so we can write k1 G1 over A1 2x over A2, where G1 and G2 are actually in Rx. By the way, notice that this is something that we can do for polynomials. What we've done is we've collected the denominators. We may not be able to do that regarding variety power systems. And so we can rewrite this equation here as and so I have A1, A2. Now, I'm going to reduce this problem a little bit in the following sense. And this is using some of the kind of stuff that we did earlier when we proved that polynomial ring over a UFD is UFD. If P is a prime non-zero, remember, this factor out here is a constant, right? This is the constant factor here. Notice if you have a prime that's sitting in here somewhere, then P divides G1x, G2x. But we saw actually earlier, prime in Rx as well. Therefore, I lost the generality, P divides G1x. So G1x equals P G1 prime of x with G1 and actually that's probably a horrible thing for me to do. I'm sorry about that by writing prime. I do not mean the derivative here. Right after I talk about the derivative, I use this. So let me put like a little stovetop have it on him or something so it's different. There we go. So in other words, what we can conclude here is if you have primes here, you can divide through and you can reduce f of x equals Q1 of x, Q2 of x. So in other words, I can assume that these constants out here in front never existed in the first place because they all had to divide back into G1 and G2. Right?
How do you get rid of, like, are you saying you repeat this process for every prime? That's it?
That's right. You just keep going, and you'll exhaust this because there's finitely many primes.
Okay.
Right? So now that we've gotten this far, now let the prime so P divides all the coefficients of f except for the leading one, and the square does not divide a constant term. Note that since P R0 P squared, then there's precisely one of the constant coefficients, one and only one. Okay, so both of these animals have a constant term, right? The product of the constant term is divisible by P. So one of those constant terms has to be divisible by P. But that's it. Like, let's suppose that the constant term of G1 is divisible by P. That means it only has one power of P in it because of this condition. It also means that if P divides the constant term here, P does not divide the constant term here, right? That's this is actually very kind of central to the proof. About loss of generality. we say that P divides constant terms, so that G1 and C1. Okay, so let's write this down here. Um, right. Since P does not divide the original polynomial f of x, the coefficients of both G1 x and G2 x are not divisible by P. So let we're going to write Q1 of x this way. A0 plus A1 x. I guess I should say in here. And we'll write G2 equals so I'm going to write the factors of F, G1, and G2 this way. Where AK one of X not divisible by P. So let me take you through it. We already know that P divides A0, right? That was our assumption here. And P can't divide all these coefficients because if you've got a factor of P all the way through here, then you have to have a factor of P and F, right? So at some point, there's got to be no P, and we'll say that this is the smallest point, or the smallest coefficient with respect to degree, where there's no factor of P. And notice that P is 0, the GCD of P and the constant term for G2 is 1, as is a K. Now, look at now let's look at the K3 term of it. F of x. So that should be A0 BK plus A1 K minus 1 plus A2 K minus 2 B1 plus A K minus 1 B1 plus A K 0. Now notice our assumption is all these A's are divisible by P. So this chunk right here is divisible by P. And this is relatively prime. Therefore, the take term of f of x is not divisible by, because this one piece is relatively prime. Right, and again, P is prime, so you can't pick up the factor of P by multiplying two things that are relatively prime. And K is less than the degree of F, which is the degree of F is what, M plus. Which is, right, K is strictly less as M is at least one. And so that does it. This contradicts the fact that all the coefficients of F up to the last one have to be divisible by. Okay. Any questions on that? Any questions? Okay. So for the last little bit, just for fun, we're going to talk a little bit about Noetherian. How many of you have ever heard this Ethereum ring? It's named after maybe my favorite mathematician, Emmy Noether. I believe it was her that was attributed the quote, "abstraction simplifies," which is not completely true 100% of the time, but it's true very surprisingly often. Anyway, rings that are Noetherian are ones that, well, for example, a lot of research, if you see things that are done in computational algebra, things like this, almost always they're looking at Noetherian rings. And there's a reason for this. Now, here's the classical definition, which may look a little bit opaque at first. Yeah, you can talk about rings that are not commuted as well, but I'm going to do this here. Let R be a commutative ring. The following conditions are equivalent. And the punchline of this, so here's a spoiler alert on this theorem. The spoiler alert is any ring that satisfies any one of these equivalent conditions, we're going to call it a Noetherian ring. The first one, I think, historically is the classical one. Hey, every ascending chain R And I guess here I mean accountable chain then, don't I? Stabilizes. And what do I mean by stabilizes? I mean, there exists K, or there exists N such that I K equals I N. All K greater than or equal. So in other words, you can't go up forever. You keep going up, and you'll eventually reach a point where the ideals have to stabilize. Right? So there is no, another way to put this is, there is no strictly ascending chain of ideals. You know, this is a notion sort of like a compact set or normal subgroup, where I think the person that first kind of noticed that this was important was, it was kind of a stroke of genius. This is equivalent to every ideal in R is finitely generated. This is why people that like doing computational commutative algebra, combinatorial commutative algebra, homological algebra, a lot of times, they like Noetherian rings, because all of their ideals are going to generate a finite number of generators. So you do computation that you can actually put your hands on the generators and do stuff. And see, in the theme of some of the stuff we've done before, and as I've alluded to before, this is actually kind of a big sign that this is an important property if it's determined by the prime ideals. The cool thing about this is every ideal is finitely generated, meaning they're all finitely generated. This is equivalent to saying every prime ideal is finitely generated. What's the use of that? They're usually there's a lot fewer prime ideals in a ring than ideals. And this last condition says, to check if it's an Ethereum, all you got to do is convince yourself that all the prime ideals have this property, which is very, very cool. And the argument is, how would you show this, by the way? So I'll outline an argument for you here, although we won't really go into it, but here's the argument. This implication is clear, right? Because of every ideal is finitely generated, every prime ideal is. You need to show that if there exists an ideal that's not finitely generated, there must exist a prime ideal that's not finitely generated. That's how you get the equivalence. What do? You assume that there is an ideal that is not finitely generated, and then you take an ideal that is maximal with respect to that property. So there's a Zorn's limit thing where, given an ideal, you look at all the ideals that contain it and are not finitely generated, take the union of that, show that any chain has an upper bound. And so now you've got an ideal that's maximal with respect to not being finitely generated, and then show that that's prime. It's similar to B or C on this week's homework, something like that. Let me throw in something real quick, just for fun. You know, the original definition about ideals stabilizing, right? So this basically says that, okay, there's no strictly ascending chain. Why are these two equivalent? Why are A and B equivalent? Well, let me kind of take you through that. Again, B implies C is obvious C plus B is that business that I was talking about. I challenge you to, try to do this, show that any ideal is maximal with respect to not being finitely generated must be prime. Why are these two the same? Why are A and B the same? Well, okay, suppose you have the ascending chain condition. You want to show that every ideal is finitely generated. So, not finite. Let me show you how you would construct an infinite ascending chain. Let's say A0. Let A0 be an element of A. The ideal generated by A0 strictly contains an I. Because after all, I is not finitely generated, and if you had an equality here, then it would be principal in fact. Select A1 and I minus A0. Notice that again, this is strict because A1 is not an A0, and this is strict because I is not finitely generated. And so now you've got A0, A0, A1, A0, A1, A2. Notice that if this process ever terminates, then I is finitely generated. So this gives that A implies B. Right? Now, on the other hand, what about B implies A? Why is this an equivalence? Every ideal is finitely generated. Take the ascending chain of ideals. Now, I claim that every ascending chain of ideals has to stabilize. So consider actually I'll start this at one, it doesn't matter. Now, how am I going to show this thing stabilizes? Well, let's let I be the union of this chain. Now, again, as I pointed out a number of times, a union of ideals does not have to be an ideal, but here we're good to go because it's a chain. We proved that a union of a chain of ideals is an ideal a number of times using this kind of zones limit stuff. And what do we know about this ideal I? It's finitely generated. what I suggest, the smallest, well, okay, alpha sub j be minimal such that j is in alpha sub j. What do I mean by that? Well, what I mean is x1 is an I, so x1 is in this union. So x1 has to appear somewhere in one of these I subscripted ideals, right? I'm going to say that x1 first appears in alpha 1, that is I sub alpha 1. x2 first appears in I alpha 2, et cetera, et cetera. Let n be the maximum of these numbers. Now, at that maximum number n, in I sub n, you have x1, x2, all the way up to xn. So, I sub n equals I. Continue to stabilize. Because once you hit the point up here in I sub n, where you've got all the generators from I, you now know that this thing is the union of all things in this chain, and so you're done. Go back, okay. And of course, the equivalence that we pointed out, this makes Noetherian rings a lot easier in a certain sense, because now, if you want examples of Noetherian rings, the NPID, right? And in fact, I'll go further. This will give you a lot of examples. Well, actually, I'm going to go ahead and give you this theorem here. Five, 7, 4. On the Ethereum, the following are also. To say a ring is Noetherian is to pay it a very high compliment. It's a very strong condition. And it's a very natural thing to ask in algebra. Okay, so I've got a nice property. How is this nice property preserved when I do some ring operations on it? So, A, localized at S, where S and R multiplicable closed set. That's good. So localizations of Noetherian rings, Noetherian, R mod I, where I and R is triangle. Fantastic. So homomorphic images of Noetherian rings are Noetherian. Both of these are not difficult to show. Additionally, if R has identity, then the following. Hilbert basis theorem. And we won't have time to prove that in this class. We did this in the commutative algebra class. And in fact, not only this, by induction, our polynomial ring in any finite number of indeterminates over an Ethereum ring is Ethereum. By the way, when I say if R has an identity, it really needs it. And what I mean by that is if R doesn't have an identity, I don't care if it's a finite ring. If R doesn't have an identity, well, it has to be a non-zero ring. If R is a non-zero ring that doesn't have identity, then Rx is never Noetherian. There's always ideals that are not finitely generated if you don't have an identity. And also power series, any finite number of variables. So, for example, any PID, any principal ideal domain, it's an Noetherian ring. Any polynomial ring over a PID and any number of variables is an Noetherian ring. If you take a quotient of that, so if you have a homomorphic image, so if you can realize any ring as a homomorphic image of a field or a Noetherian ring in a finite number of variables, it's automatically Noetherian. So there's a lot of them out there. Let me ask you all kind of a quick question here. Definition. We say a ring is Artinian. Ethereum named after Noether, Artinian named after Art. If every descent By the way, here's a quick question for you. Is one of these conditions stronger than the other? Are they totally unrelated? Did anybody think of a Artinian ring that's not Noetherian, or an Ethereum ring that's not Artinian? Let me point this out. Z is a PID. Every ideal is principal, so for sure it's Z. That chain of ideals never stabilizes, does it? Always getting smaller, never zero. So Z is Ethereum, but it's not Artinian. Do these things exist in the real world? Yes, they do. Artinian rings. For example, any finite ring has to have this property. Here's the theorem. So here's what I'll leave you with. Is Artinian. If and only if R is Ethereum, dimension of R is 0. And remember, what this means is all prime are not. So in other words, an Artinian integral domain must be a field because the zero ideal is prime there. This is Max. Okay, any questions on that? Any questions? Okay, I will start the process of getting a review session for us Monday at 5:30. I encourage you all to get the math in. I should be able to finish up your homeworks today. Don't forget you got your last one to be turned in today. Let me know if you're having trouble with that. Other than that, once my student, always my student. If I can help you out in the future, let me know. Y'all have a good one, and we'll see you hopefully before the final. Rock on.